In this video, we're going to have a little more practice with the definition of a subspace by proving that the sum of two subspaces and the intersection of two subspaces are again subspaces. So let's begin by defining what the sum of two subspaces is. If you have subspaces x and y of a vector space V, then we define the sum x plus y to be the set of all things which you can get by adding something in x to something in y. And what we will prove is that x plus y is again a subspace of V. So remember, the less than or equal to notation here means is a subspace of. And if we're going to prove this, we have to check the three parts of the definition of being a subspace. The first of which is that a subspace must contain the zero vector. Now, x and y are subspaces, so they contain the zero vector. So 0v plus 0v is an element of x plus y, since x plus y consists of all of the things you can get by adding something in x to something in y. But of course, the zero vector plus the zero vector is the zero vector. That's part one of the definition of subspace. Part two is closure under addition. I have to take any two things in x plus y and prove that their sum is an x plus y. So let's let xi plus yi be in x plus y for I equals 1 and 2, where of course I intend xi to be an element of x and yi to be an element of y. Okay, so those are two typical elements, two arbitrary elements of x plus y, and now I have to show that their sum is in x plus y. But if I take their sum, x1 plus y1 plus x2 plus y2, then because vector addition is always associative and always commutative, so those are part of the definition of being a vector space, those are vector space axioms, I can rewrite this as x1 plus x1 plus x2 plus y1 plus y2. Now, if you look at this part here, this is an element of x, as x is closed under addition. It's a subspace, so it's got to be closed under addition. Similarly, if you look at this part here, this is another element of y, because y is a subspace of V, and therefore y is closed under addition. So this is something in x plus something in y, therefore it's in x plus y. We've shown that x plus y is closed under addition, so we've got one more thing to do, which is closure under scalar multiplication. So we'll choose a scalar. So a scalar means an element of whatever field the vector space V is a vector space over, so it's an element of whatever field we're allowed to do scalar multiplication by. And we need to choose an element of x plus y, so we will choose little x plus little y, where of course, as usual, this will denote an element of x and this will denote an element of y. Okay, now we have to show that the scalar multiple lambda times x plus y is in the sum of the subspaces x plus y. So we can do that by multiplying out. Again, one of the vector space axioms tells you that scalar multiplication distributes over addition in this sense. But now, this thing is an element of x, as x is a subspace, so it is closed under scalar multiplication. And for the same reason, this thing here is in y, as y, being a subspace of V, has to be closed under scalar multiplication. So this is the sum of something in x and something in y, so it is in x plus y. We've shown that x plus y satisfies all three conditions to be a subspace, so it is a subspace. Okay, part two, we're going to show that the intersection of two subspaces is again a subspace. So my claim is, again, if I have two subspaces x and y of a vector space V, then actually x meet y, x intersect y is a subspace. So let's take our proof. Again, we've got to just check the 3 conditions for being a subspace. Condition 1 is that a subspace must contain the 0 vector. So again, the 0 vector is in X because X is a subspace. The 0 vector is in Y because Y is a subspace. So if it's in X and Y, then it must also be in their intersection. So the intersection contains the 0 vector. That's part 1 of our proof. Part 2 is closure under addition. So I have to take 2 things in X intersect Y and show that their sum is again in X intersect Y. So let's let A and B be in X intersect Y. Okay, what can I say about A? A is then in X. B is in X. Since they're in X intersect Y, they're certainly in X. So because X is a subspace, A plus B has got to be in X again. Okay, the exact same argument applies to Y. A is in Y, B is in Y. So A plus B is in Y. Now we've seen that A plus B is in X, A plus B is in Y. So putting those 2 things together, A plus B is in X intersect Y. We have closure under addition. So the last thing we've got to do is to prove closure under scalar multiples. So we will take a scalar lambda and we will take any element little a in X intersect Y, and we can just play the same game. A is in X, X is a subspace, so X is closed under scalar multiplication and lambda A is therefore in X. The exact same argument applies for Y, so lambda times A is in Y, and putting those 2 together, lambda A is in X, lambda A is in Y, so lambda A is in X intersect Y. We've shown X intersect Y is closed under addition, closed under scalar multiplication, and contains the 0 vector, therefore it's a subspace.